I am Miss Amanali, and today we are going to study another lecture of design and analysis of algorithms. In our last lecture, we discussed about what is an algorithm, why do we need algorithms. Then we discussed that how do we analyze algorithm, what are the things we considered while analyzing the algorithms. We also discussed that why analysis is important. So this is just a little recap of what we have already studied. So why we need analysis? The answer is very simple, that if we have two algorithms, how do we choose the best one? So for choosing the best one, we have to analyze the algorithm. And designing also contains a lot of things, a lot of techniques and a lot of principles to be considered while designing the things. So basically, when we say that we are analyzing the algorithms, we are basically analyzing the performance of algorithm, and obviously the performance of algorithm directly affects the performance of your computer, of your machine, of whatever you are building, whatever it is, a software, an application, a game, or anything like that. If the algorithm used at the back end is good enough, is fast enough, then whatsoever you are building would also be a very good thing. It will be a very efficient. So why performance analysis? But there are many important things that should be taken care of, like user friendliness, modularity, security, then maintainability, etc. Then why to worry about performance? Obviously the answer to this is simple. We can have all the above things only if we have performance. So performance is like currency through which we can buy all the above things. And another reason for studying performance is speed. So to summarize, basically performance is actually equals to the scale, like what scale you are building an application. So just think about it. If your computer is not providing good performance, let's take an example. Let's imagine a text editor that can load 1000 pages but can spell check 1 page per minute. It means 1000 minutes for 1000 pages. Can anyone wait that long for spell checking? Obviously it is not possible. It is too much time taking. Or just consider an image editor that takes 1 hour to rotate your image to 90 degrees, left or right or whatsoever. Or just consider about other examples, like your computer taking 5 minutes to turn on and 5 minutes to shut down, your music video taking 5 minutes to load. So it is very time taking, and if something is taking that much time, you just simply come to a conclusion that these things are not good at performance. So if a software features cannot cope up with the scale of task user needs to perform, it is as good as that. So let's think about it, that we have two algorithms for tasks. How do we analyze it? How do we find out which one is better? The one way of doing this is to implement both the algorithms, run the two programs on your computer. It means you pick up these two programs and you just take up two different inputs, you take up two different machines and you just run them, and then you analyze that which of the algorithm takes less time. But there are many problems with this approach. First of all, let's say that if as a common person I am going to analyze an algorithm and I just have one machine. So first of all I will run the first algorithm, then I will run the second algorithm, and it will take a lot of time and it's a hectic thing. I mean, this is not a time-saving technique. Other problems contain, like just for example, it might be possible that for some inputs first algorithm performs better than the second, and for some inputs second performs better. Like there could be set of two inputs, input 1 and input 2. Maybe first algorithm picks up input 1 and performs better, but if we give the same input to second algorithm, it doesn't perform well. Like different input on different inputs, the algorithm will perform differently. Similarly, on different machines, it might be possible that for some inputs, first algorithm perform better on one machine and the second works better on the other machine. These two things mean that your algorithm can be performed, its performance will differ on different inputs, its performance will differ on different machines. हो सकता है आप सेम इनपुट दें लेकिन machines different हो. So when machines are different, algorithm will perform different. It simply means that this way of analyzing an algorithm is not the efficient way of analyzing an algorithm. So we just came to the main topic. The main topic which we are going to study today is asymptotic analysis. This is a kind of analysis which is done for algorithms. So asymptotic analysis is the big idea that handle the above issues in analyzing the algorithms. In asymptotic analysis, we evaluate the performance of an algorithm in terms of input size. We do not measure the actual running time. We calculate how does the time or space taken by an algorithm increases with the input size. We simply think that we have an algorithm and we just assume that let's suppose I have an algorithm and I have to sort some numbers. So what will I do? I will just think that if I give n input, n is the size of input. I explained it earlier that n is the size of input means let's say my input has 100 numbers. If my input has 100 numbers and I just say that its size is n and it will keep on increasing. I can increase it to 200 numbers, 300 numbers, 1000 numbers or anything like that. When the size of input will be increased, I have to check that how my algorithm size increases. The function of which calculates the time increases. We will discuss it later, you will understand it. For example, let us consider the search problem, searching a given item in a sorted array. One way to search is linear search. So the growth rate is also linear. The other way is binary search. These are two searching algorithms, linear search algorithm and binary search algorithm. Now these two searching techniques have a growth rate. The linear search has linear growth rate and binary search has logarithmic growth rate. Now what if, to understand how asymptotic analysis solves the above mentioned problem in analyzing the algorithm, let us say that we run the linear search on fast computer and binary search on slower computer. For small values of input array size n, let's say if we just picked up small array like 10 numbers or 20 numbers, the fast computer may take less time. It will just sort out the array very easily. But after a certain values of input array size, it simply means that what if I just input 100 numbers and then 1000 numbers and then million numbers and then trillion numbers. In that way, binary search will definitely start taking less time compared to the linear search, even though the binary search is being run on the slow machine. Now you can see that we run the linear search on a fast machine and binary search on a slow machine. But because linear growth rate is higher than logarithmic growth rate, that is why our binary search will take less time. The reason is the order of growth of binary search with respect to the input size is logarithmic. Now you can see next day, this is the graph. Now you can see here time, here in this graph we are representing how the growth rate is represented in this graph. Now you can see logarithmic growth rate is much lesser than the linear growth rate. And this orange, or you can say yellow line, represents exponential growth rate, this O raised to power n, or you can say n square. I'm sorry, it's O n square. So this is something very high. This growth rate is very high. Logarithmic growth rate is the lowest growth rate. It increases very slowly. Linear increases comparatively on a larger scale, and exponential just goes up in a very fast way. So the machine dependent constants can always be ignored after certain values of input size. We do not consider the machine dependent constants. Now, what are machine dependent constants? Whatever things which are depending on the machine, these are not considered when we are doing analysis and all that stuff. So does all asymptotic analysis always work? Now, it's not perfect. It cannot be perfect, but that is the best available way for analyzing the algorithm. Why it is not perfect? Because everything has some drawbacks, some loopholes, or things like that. For example, say that there are two sorting algorithms that take 1000 n log n and 2 n log n times respectively. Now you can see that the 1000 and 2, these are constants. So both of these algorithms are asymptotically same. Order of growth is n log n. So with asymptotic analysis, we cannot judge which one is better as we ignore the constants. As I explained earlier, and I said that machine dependent constants and other constants, many constants, whatever. Okay, just consider about the constants which are present in your mathematical formulas. So constants are ignored in asymptotic analysis. So that is why you can see that there was 1000 n log n and 2 n log n. If we analyze them asymptotically, they are the same. So it means that it can take more time than 1000 n log n will take more time than 2 n log n. But asymptotically, if we analyze it, we will have the same answer, that they have same growth rate. So there is none of them is better. Another problem is that we always talk about input size larger than a constant value. Whenever we are talking about asymptotic analysis, we are considering a massively large input of size, like in millions and trillions of numbers and all that stuff. So it is might possible that those large inputs are never given to your software, and an algorithm which is asymptotically slower always performed better for your particular situation. What if your machine never gets that large inputs? You have analyzed the algorithms on the basis of like you think that you will be giving your algorithm trillions of numbers, and when your software is being made, the software is always about to sort 10 numbers, 20 numbers, 30 numbers. So just consider that you had two algorithms. You choose the algorithm which has a slower growth rate, but if the other algorithm has a faster growth rate, but for smaller inputs it works very well. But you didn't choose it because it was having a larger or a very faster growth rate, and your machine never gets the bigger input size, bigger inputs, larger inputs. It always works on the smaller inputs, and for smaller inputs the algorithm with a greater growth rate was also very fine. So that is also a very big problem, that maybe for your particular situation the algorithm you choose is not the best suited, but asymptotically you choose, so you have to go with it. So you may need to end up choosing an algorithm that is asymptotically slower but faster for your software. So these are the things when you simply implement the things practically. So at that time you have to make different decisions depending on what is your requirement according to your situation. Okay, so we are going to have Asymptotic analysis overcomes the problem of naive way of analyzing algorithms. So basically, we use asymptotic analysis all the time, so we will see that what it does. I also explained it earlier, but now we will study it in detail. So we can have three cases to analyze an algorithm. We will have the worst case, the average case, and the best case. Now let us explain it using a linear search. Let's say what would be the worst case analysis. That is usually done, worst case analysis. In worst case analysis, we calculate upper bound on running time of an algorithm. We must know the case that causes maximum number of operations executed. Now what do we mean by that? We simply mean that we will say how much maximum time your algorithm will take and what could be the situation in which much time will be used. Now let's say for the linear search, the worst case happen when the element to be searched is not present in the array. Let's say you have an array of 10 numbers or 20 numbers or whatsoever. Let's say it is the array of 10 numbers and it has 1 to 10 numbers. Now you just enter search a number like say 19 and it is not in the array. So the worst case analysis would be that it will search all the array, it will compare it with all the numbers, and it would be the worst case analysis. Worst case is that you have to do all possible comparisons. So when x is not present, let's say x is a number, like x is was 19, the search function compares it with all the elements of array one by one. So the worst case time complexity of linear search would be theta n. Now we will discuss theta n later in this same lecture, then you will understand what is that theta n. Then we have average case analysis. That is sometimes done but not mostly. In average case analysis, we take all possible inputs and calculate computing time for all the inputs, sum all the calculated values and divide the sum by total number of inputs. We must know or predict distribution of the cases. Now this average case analysis is little complex. Why? Because let's say we have an array of 10 numbers. Let's say the 10 numbers were from 1 to 10. Now what will we do? That we will take each number. I will take 1. I will see how much time it takes to sort out the 1, to find out the 1. Then I take 2, 3, 4, 5, 6, 7, 8, 9, 10. Now for searching all these numbers, I will have a certain. Now what will we do? We will calculate the time for each input, like for 10 inputs. Then we will sum up the time and we will divide it with the total number of inputs. So we will have an average input, average time for calculating the input. For the linear search problem, let us assume that all the cases are uniformly distributed, including the case x not being present in the array. It means that we will also include a number that is not present in the array. Let's say that is 11 or that is 19. It means that we will do like I will give input of 11 numbers, 10 numbers which are present and 1 number which is not present. I will calculate the time for all these numbers, how much time it takes to search out the number, and then I will add up all the time and I will divide it with the number of inputs. So in that way, average case complexity will be found out. Then we have best case analysis, and it is sometimes it's called bogus analysis because that is not useful. It is not much useful. Now what is this? In the best case analysis, we calculate lower bound on running time of an algorithm. It means the minimum time an algorithm will take. We must know the case that causes minimum number of operations to be executed. In the linear search problem, the best case occurs when x is present at the first location. Let's say if I had an array of 10 numbers 1 to 10, it simply means that I am now searching for 1 and 1 is present at the first place as a first location of an array. So the number of operation in the best case is constant, not dependent on n. So the time complexity of best case would be theta 1. It is simply the very less time. It is taking very less time to calculate it. So most of the time we do worst case analysis to analyze an algorithm, because in worst case analysis we just guarantee an upper bound on running time of an algorithm, which is good information. We just say that what could be the maximum time one algorithm will take. This is what we are concerned about. Like, we are not concerned about how much less time an algorithm will take, because we always consider the worst case and we prepare our machines for that. The average case analysis is not easy to do in the most of practical cases. It is rarely done. Why it is not easy to do? Just think about it, that right now I talked about 10 values, and for linear search. What if I have 20 inputs, like 20 numbers in array, 30 numbers in array, and what if I have millions of numbers in array and I have to do the searching and sorting? How would I prepare all the searching, all the inputs to be searched, and then I will calculate all the time, and then I will sum up all the time, and then I will divide it with the input? It is a very complicated thing. So it's a little complicated thing, but it is done wherever required. But the worst case does all the work. So the best case analysis is bogus, guaranteeing a lower bound on algorithm that doesn't provide any information. We do not need it. Maybe we just get a best case analysis and the bound is very low, and when we run it on algorithm on a big size of input, it just takes years to run. Yes, one other thing which I thought that I missed in the lecture was that upper bound and lower bound. What I said, that upper bound is the maximum time, lower bound is the minimum time. This is an example that might explain you that what if you have a number, there is something that weighs approximately 7. So upper bound would be 7.5 and lower bound would be 6.58. It means that maximum for some algorithm, all cases are asymptotically same. There is no worst case, there is no best case. Like for example, for merge sort does theta and log and operations in all cases. If you do it in the worst case, or you do it in the best case, or it's an average case, so it doesn't matter. But most of the other sorting algorithms have worst cases and best cases. So for example, in the typical implementation of quick sort, where pivot is chosen as the corner element, the worst occurs when the input array is already sorted, and best occurs when the pivot element always divides the array into two halves. If you know about the quick sort, you will understand that we just choose a pivot element that divides the array into two halves, and then we switch the places. If you have not studied quick sort, you need to study it on internet. You will find it very easily. So whenever the corner element is chosen, it's a very big problem, because it will never divide your array into a comparatively better halves, and that is why it will take more time. So that is not a good choice at all. So for insertion sort, the worst case occurs when the array is reverse sorted, and best occurs when the array is sorted in the same order as the output. Now these sorts must be understood by you already. I think you have studied data structure before you just came to this subject. So we have discussed asymptotic analysis and the worst, average and best case algorithm. The main idea of asymptotic analysis is to have the measure of efficiency of an algorithm that does not depend on the machine specific constant and does not require the algorithm to be implemented and the time taken by the programs to be compared. Just think about it, that how will you choose an algorithm if you implement it practically? First of all, you will pick up an algorithm, you will simply make a program using that algorithm, then you will run the program and you will calculate the time. It's too much time taking, and it is not a best practice at all. So that is why asymptotic analysis is done, because it do the things efficiently and obviously not perfectly, but much efficiently. So asymptotic notations are mathematical tool. Now asymptotic notations are used in mathematics, and they are mathematical tools to represent the time complexity of algorithm. So we have we have actually 5 asymptotic notations, but 3 are commonly used, and the last 2 are also used, but they are not that much efficient as the starting ones are. So we have these 5 big notations. This is called big O notation. This is theta notation. Then we have big O notation. Then we have big omega notation. And then at 4th number we have little o asymptotic notation and little omega notation. So if we talk about the first one, it is kind of average case analysis, and this is kind of best case analysis. No, sorry, this is worst case analysis, and the lower bound is best case analysis. So first we will talk about theta notation. So the theta notation bounds a function from above and below. So it defines exact asymptotic behavior from the above and the below. It simply means it is taking the best case and the worst case, and it is kind of making something average. The simple way to get theta notation of an expression is to drop the low order terms and ignore the leading constants. We just simply drop whatsoever is so small, and we also drop the constants. We will see it in an example. Let's say this is an example. You can see that, let's suppose this is in some mathematical expression, and it belongs to theta notation. So what we will do, we will drop the lower order terms because we do not need it. Like there will always be a n0. N0, you can say that it would be the smallest value. We will just consider the highest variables with highest exponential values, like n raised to power 3. So we say that theta notation is n raised to power 3 because it has higher values than n raised to power 2 and the rest of the things, and constants are to be dropped. So we can take another example. That is, we take another example, that if for some algorithm the time complexity is represented by an expression 3n squared plus 5n. So we use the big O notation to represent this. The time complexity would be simply we will take n square, and we will ignore the 3, and we will also ignore the insignificant part, that is 5n. 5 and 3 are ignored because they are constants, and n square is considered because whenever you reach n square you pass by the n. So here the example above, the time complexity of theta n square means that the average time for an input n will remain between k1 into n square and k2 into n square. Now k1 and k2 are the constants. So simply we can say that these are actually binding the expression, and it is binding the growth of the algorithm. So this paragraph, this graph will explain more, that we have simply k1 into fn, k2 into fn, and running time is between the upper and lower bound. So this is something which I need to explain you. This is some formula that represents this theta notation. It simply states that if there is a theta notation, we have fn a function, there are positive constants c1 and c2, such that the main thing is this, you need to understand only this thing, that 0 is less than or equal to c1 into gn, which is less than or equal to fn, which is less than or equal to C2 into Gn. It simply means that this would be considered a kind of upper bound or lower bound. These two are considered the upper or lower bound, and the function is between these two things. It is an average thing which lies between upper and lower bound. So the above definition means that if fn is theta of Gn, then the value fn is always between C1 into Gn and C2 into Gn for the larger values and non-negative values. So we mean that the time complexity represented by theta notation is like average value or range within which the actual time of execution of algorithm will be. The actual time between the best and the worst, the average thing, that is mostly the average thing and mostly the actual execution of an algorithm. Then we have the second one, that is big O notation. The big O notation defines an upper bound of an algorithm, the maximum time an algorithm will take. It bounds a function only from above. It does not have to take care of what could be the lower bound and what could be the minimum time taken by the algorithm. For example, consider the case of insertion sort, like linear time is best case and quadratic time is worst case. Linear time is less and quadratic obviously the more time it is taken. So we can safely say that time complexity of an insertion sort is n square. Note that n square also covers the linear time. Now n square is worst case complexity. Now this is worst case complexity. It means it is quadratic and it also covers the linear. This notation is known as upper bound of the algorithm or worst case of an algorithm. It tells us a certain function will never exceed a specified time for any value of input. It simply means it gives a limit that this algorithm will take that specific time and never more than that specific time. It gives us a limit that this algorithm has this worst case complexity, this worst much time, or maximum this much of time will be taken and it will never exceed this time. So the question is that why we need this representation. We already have an average notation which represent a tightly bound running time for any algorithm. We know what is average time and we actually know what is actual running time. As I said in the theta notation, that it actually represents the actual running time or actual execution time of an algorithm. Then when we have that, why we need another big O notation? So the answer is very simple. We have an example here that consider a linear search algorithm in which we traverse an array of elements one by one to search a given number. So in worst case, starting from the front of the array, we find the element or number we are searching at the end. It simply means that is a worst case, which will lead to a time complexity of n, where n represents the number of total elements. But it can also happen that whatsoever element we are searching for is the first element of the array. It's right in the start and the time complexity will be 1. Now in this case, saying that the theta notation or the tight bound of the time complexity will be theta n will mean that the time required will always be related to n. As this is the right way to represent the average time complexity, but when we use big O notation, we mean to say that the time complexity is On, which means that the time complexity will never exceed n. Here we say the actual running time, the average running time. But when we say big On, we simply say that no matter whatsoever happens, your algorithm will not take more time than the one we already described. So that is why it is a very useful and it makes more sense. So if theta notations are to be represented time complexity of insertion sort, we will have two cases. The worst case will be n raised to power 2 and the best case will be only n. But in big O notation is only useful when we need only the upper bound. We do not care about the best or anything like that. Similarly, as I explained the theta notation, we have again the function of this. All the things are same. Now here we can see that we have 0 less than f of n, which is less than c systolic g of n. It means f of n is always less than or equal to the worst case, the maximum number of time, the maximum number of operations, or the maximum time one input or one algorithm will take. Now we have omega notation or big omega notation, the third one. The big omega notation is used to define the lower bound. It is the best case of an algorithm. This always indicates the minimum time required for any algorithm for all input values. Therefore, it is the best case for an algorithm. In simple words, when we represent a time complexity of an algorithm in the form of big omega, we mean that algorithm will take at least this much time to complete its execution. It means never less than that. Even if you are searching for one number and it is in the first place of your array, so it takes 1 second, so that 1 second is the best case analysis or the lower bound. And if you search for a number that is not present and it takes 10 minutes, so that 10 minutes is the worst case analysis, because it will never take more than that time, or it is upper bound. So omega notation is the least used notation because it is not useful. We are not always lucky enough to have a number always in the start of the array and all that stuff. So the function to represent the omega is that 0 is less than g of n, which is less than f of n. It simply means that f of n is on the lower bound. So we have little o notation or asymptotic notation. So big O is used as a tight upper bound on the growth of an algorithm's effort. This effort is described by the function fn. Even though as written, it can also be a loose upper bound. So if we have a loose upper bound, we simply say that it is little o notation. It is simply used to describe an upper bound that cannot be tight. It means it is not exact. It is loose value. So let fn and gn be functions that map positive integers to positive real number. So simply we can say in mathematics that loose upper bound is simply shown as that if sometimes f of n is equals to big O into g of n, and when we divide these two we get the answer of 0. So it is a this is here, that 0 is less than f of n, which is less than c into g of n. This is something we say it is, and it is not, mostly it is not used. It is not that much significant. It is not that much useful for our algorithms and for our analysis. Then we have little omega representation. It is also the loose lower bound, not exact lower bound, but the loose lower bound. And how it is represented? It is represented f of n greater than c into g of n, which is greater than 0. So f of n has a higher growth rate than g of n. So main difference between big omega and little omega is their definitions. In the case of big omega, we have this. Alright, this is not something to be worried about because we are going to compare it as a table that is here. Here you can see that we have written down all the functions which we have studied. So you can compare them, and you can see that between big O and small o, we have a tight upper bound, and there we have a loose upper bound. And similarly in small omega and large omega, small omega and big omega, whatsoever you have studied, like the functions like that, they are not that much complex. You might find it complex, but with the passage of time, with the more detailed explanations, you will understand that these are not very difficult things, and you will understand them very easily in the coming lectures. And even you all have the facility of internet, and you can search these things on internet as well. So right now this is the last slide of my lecture. I have completed all of my lecture. The main thing I would say again is that which I said in my last lecture as well, that if you are having any questions, please write down your questions in comment, or if you have any questions and you are not writing down them in comments, please you can mail me on my email address which is given there, and I will also give it as a link, and I will surely answer your questions by reading your comments and reading your mails. We will have a session on Zoom if the questions are not you're not getting the answers. I will also upload the answering videos, but it depends that you do the question, because right now you're not doing questions, and I will answer the mails and the comments and all the stuff. So it is better you will see all the video, as I can see the views on the video and I can also see the viewing time. So the viewing time tells me that how many of the students are watching the video and they are following all the instructions. So if all the questions are welcomed, you can question, you can mail me, you can message me on the Zoom, you can ask through your CR. I will send you the voice notes, I will upload the videos of answering the question. The specific topics you do not understand, I will upload the video of that specific topic on the YouTube. So do not worry about how you will get answers. You will get all the answers, and I will try to satisfy you in all the ways. So please follow the instructions. Thank you very much.